one, give me 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 one.
Hello everyone, this is Swathi, working as assistant professor in the Department of Electronics and Communication Engineering in Institute of Aeronautical Engineering, Dundigal. Welcome to this lecture. In this lecture, we'll be discussing about the serial adder, binary adders, various types of binary adders. In that, we'll mainly concentrate on serial adder, parallel adder, and carry look-ahead adder. And also, we'll look at the comparator and what are the different types of comparator and what is a comparator. So, how to construct a comparator using logic gates, we'll discuss in this lecture. So, first, let us see what is binary adder. So, as we all know that full adder and half adder can perform the addition of two 1-bit numbers. So, half adder can perform the addition of two 1-bit numbers, whereas the full adder can perform the addition of two 1-bit numbers and one input carry. So, but a serial adder or parallel adder is a digital circuit which is capable of performing arithmetic operations like addition and subtraction of two binary numbers which is having more than 1 bit. That means the binary adder or we have two types of binary adders, basically serial adder and parallel adder, right? So these are the combinational logic circuits which can perform the addition of two binary numbers of more than 1 bit each. So the serial adder or parallel adder is a digital circuit capable of finding the arithmetic sum of two binary numbers that is greater than 1 bit in length by operating on corresponding pairs of bits in serial or parallel. So what is serial and parallel? Serial means performing the addition of bits serially bit by bit. That means adding two numbers bit by bit in serial fashion is known as serial addition. So if all the bits are added at a time, that addition is called as parallel addition. So first let us see what is a serial adder. So serial adder is a circuit which can perform the addition of two binary numbers of more than 1 bit each by adding bit by bit from LSB to MSB in serial fashion. For doing this, we need only a full adder. That means it requires only one full adder. So with respect to one full adder, we can perform the addition of two binary numbers which are of length more than 1 bit each. So how can we do that? What is a logic circuit? What is the logic behind this serial addition? So as I told you that we will be adding in serial addition, we will be adding one bit by bit in serial fashion. So here the circuit diagram of serial adder is as shown in figure. This is the circuit diagram. So where it requires only one full adder and an additional circuitry which is nothing but a delay circuit. So the delay circuit and a full adder forms a serial adder which can perform the addition of two binary numbers of more than 1 bit each. So as we all know that full adder can perform only the addition of two binary numbers of 1 bit each. But by using the same full adder, we can even perform the addition of two binary numbers of more than 1 bit. How we can perform the addition of two binary numbers? By using a full adder whose length is more than 1 bit. Okay, so here this is a serial adder circuit which is having one full adder circuit. So as we all know that full adder requires three inputs A, B and C in, which is a carry input from the previous section, and anyhow the addition results two outputs. One is the sum output and the other one is the carry output. So for example, if you are adding two 3-bit numbers or else two 4-bit numbers each, so that is A is equals to A3, A2, A1, A0, and similarly B is also equal to B3, B2, B1, B0. So I want to perform the addition of these two binary numbers of 4-bit each. So now the addition can be performed bit by bit starting from LSB to MSB. So first A0 and A0 and B0 are added, and if any carry is resulted, then that carry will be forwarded to the next section, and then we are going to add C in A1, B1, and again this results some bit. Let us consider the sum of these two will be S0 and the sum of these will be S1, S2, S3, and finally we may have a carry. So we may have carry from this section to this section. Let us consider this as C0, and this one, the sum of these may result as C1 and some of these may result as C2, and thus final addition of the C2, A3 and B3 will result as sum bit as well as carry, and the carry bit is considered to the C out, whereas the sum is of 4 bit. So that means by adding two 4-bit binary numbers, I will get 4-bit sum and 1-bit carry. So this is the output. So now how to perform the addition of these 4-bit binary numbers using the serial adder. So here, as I told you that we are using only one full adder initially, this works in synchronous with the clock pulse. So as we know that this serial adder operates in synchronous with the clock pulse because we have a delay circuit. So basically the delay is nothing but a flip-flop. Okay, so as we all know that flip-flops are sequential circuits which operates in synchronous with the clock pulse. Okay, so the numbers to be added or applied at the input bit by bit and then added. So when we add the number when we add 2 bits, so it can produce sum and carry. So the carry will be forwarded to the next addition. So in order to store that carry, we are using here delay. So this delay is used to apply the carry output of one section of addition to the next section of addition here. That means initially we will be sending LSBs. When we are adding LSBs, we need to consider the carry input as 0. We need to consider the carry input as 0. So here initially the circuit will be in reset position. In reset position means S0 will be 0 and Cin will be 0. So that will be coming as the third input to the full adder. And now the 3 inputs along with the 2 LSBs of the 2 binary numbers and the carry input, which is a 0, are added using full adder. So then it produces some S0, and this will be stored in some storage device like buffer or register we will be using for storing the sum, because we are applying the input serially, and we also take the output bit by bit, so in serial fashion. So in order to store the bit of data, we need to have a storage device. That storage device may be a register or it may be a buffer. Okay, so here during the first clock pulse, LSBs are added. And during the first clock pulse, the carry input is considered to be 0, which is given as input, third input to the full adder, so that it produces the sum S0 and carry C0. So this carry will be given as input to the delay circuit. So most commonly we will use D flip-flop, where D flip-flop is a data flip-flop which can store the data and with the data only given as output. So during the first clock pulse, so carry input is 0 and the LSBs are added. So the sum output is stored in the register or some other storage device, and the carry output of this LSB bits is stored in delay circuit. And during the next clock pulse, so what happens? The next bit of the 2 numbers, that is A1 and B1, are given to the full adder. And at this time, the carry which has been stored in the delay circuit is now applied here. That means C0 is given as the input to the full adder along with A1 and B1. So now the full adder performs the addition of A1, B1 and the carry from the previous addition, that is C0, and produces the sum S1 and also the carry C1. So the sum S1 again moved to the storage device and C1 is moved into the delay circuit. And during the third clock pulse, this is during the second clock pulse, during the first clock pulse. So during the third clock pulse, this delay circuit outputs the carry, that is C1, which is given as the input to the full adder. Now C1 comes. So C1 is a carry input which is already stored in the delay circuit, and now the third bit, that is A2, beta, are applied to the full adder. So it performs the addition of A2, B2 and C1 and produces some S2 and carry C2. So this process repeats until all the bits of two numbers are added. So that means here we need an extra circuitry, which is a delay circuit, which is nothing but a D flip-flop, okay, which can be used as a delay or else data flip-flop. So it can be used to store the carry from the previous section, and it is given as the input to the full adder, so that it performs the addition of 3 bits and produces the sum and carry again. So like that, the bit by bit are applied to the inputs of full adder, and the addition is performed, and the sum bits are stored here. This is the serial adder. So here let us have a brief recall of the operation. So as I told you that this serial adder operates in synchronous with the clock pulse. The numbers to be added are applied at the inputs bit by bit and then added. So the inputs are applied bit by bit to the full adder and then performs the addition. And the first two LSBs are applied at the inputs of the full adder during the first clock pulse. And the third input during the first clock pulse, the third input to the full adder is considered to be 0 for the first time. So next, these bits are added to get the sum bits S0 and the carry bit C0. The sum bit is taken out and stored. So here we can use either a buffer or a register. So in order to store the sum bit produced by the full adder in each of the clock cycle. And then the carry bit is given as input to the delay circuit. When the clock pulse is given, the carry bit C0 is applied at the carry input or as the third input of the full adder along with the 2 bits of the binary numbers to the full adder to be added, that is A1 and B1. So like that, during the next clock pulse, that is the second clock pulse, C1 is given as the third input, whereas A1 and B1 are given as the inputs to the full adder and performs the addition. And again, the sum bit is generated. So that 3 bits are again added and the sum and carry are generated. Again, the sum is taken out and it will be stored in the register. And again, the carry is given as input to the delay circuit. So this process repeats until the all the bits of the 2 binary numbers are added. So here, this is achieved by the time delay circuits, and mainly the D flip-flops are used for the purpose of delay. Okay, so in the serial adder, the one full adder is adequate. This makes the serial adder economical. So as the number of components or else number of equipments required or less, so it is more economical. But in order to perform the addition of n bits, it require n clock pulses. That means we can see that the time required for performing the addition of 2 n-bit numbers is more in case of serial adder, because only one full adder is performing the addition of all the bits bit by bit. So that is why the time required for performing the addition of 2 n-bit numbers is very high. That means the delay is more in case of serial adder. So that is why we are going for another type of full adder, which is a parallel adder. So how can we get a parallel adder? So in case of serial adder, we are using only one full adder. Instead of using of one full adder, if you use n number of full adders which are cascaded together, and if you apply all the inputs to the full adders at a time, so that we can reduce the time, so that the addition operation can be performed faster. So that means we can have another type of adder, which is nothing but a parallel adder, in order to avoid or else overcome the limitations of serial adder, which is, as we are performing the addition bit by bit, it is time taking. Even though it is economical, but it is time taking. So the addition operation can be performed slower. So in order to increase the speed of adder, we are going for the parallel adder. In parallel adder, So we are the more number of full adders are cascaded together. How many number of full adders to be cascaded? How can we decide it? Depending on the number of bits in each adder, we have to take that many number of full adders. For example, if I want to perform the addition of two 3-bit binary numbers A2, A1, A0, and B is also B2, B1, B0. So I want to perform the addition of two 3-bit binary numbers. Then how many number of full adders are required? So for each bit addition, I require a full adder. So like that, I can use 3 full adders, or else. So in order to perform the addition of two LSBs, as we don't have any carry for the add while we are adding the LSBs, so we can also use 1/2 adder and remaining 2 full adders. Okay, so that means for implementing a parallel adder circuit, I can use 1/2 adder for performing the addition of 2 LSBs and the remaining n-1 full adder circuit. So that means if my two numbers are having 3 bits each, then 1/2 adder is required, okay, for performing the addition of 2 LSBs, and the remaining n-1, that is 3 minus 1, that is 2 full adders are required. Or else I can use all the 3 full adders by taking the carry input for the first full adder, which is adding the LSBs as 0. So either I can use all the full adders, or I can use 1 full adder for performing the addition of 2 LSBs and the remaining n-1 full adders. Okay, so this is a parallel adder. So in order to get a parallel adder circuit, so we need to cascade n number of full adders depending on the where n is a number of bits in each number, where either A or B. Okay, so the carry output of, so how we are going to cascade? Cascading means, always you remember, connecting the output of one circuit to the input of the other circuit means cascading. So here, which output of the full adder is going to be connected as input to the next full adder? So we have 4-bit sum. So the sum bits are taken as it is, whereas the carry output of one full adder is given as the input to the next full adder. So this is why we are calling it as cascading. Okay, so that means the carry output of the first full adder is treated as the carry input to the second full adder, and the carry output of the second full adder is treated as the carry input to the third full adder. So this is the 4-bit binary parallel adder circuit, where we are constructing a 4-bit binary parallel adder using 4 full adders. So first full adder, second, that is full adder 0, which can perform the addition of least significant bits. Next, A1, B1 are added using full adder 1, A2, B2 are added using full adder 2, A3, B3 are added using full adder 3. And this is an example of parallel adder. Why we are calling it as parallel adder? Because all the bits of 2 numbers are applied to all the full adders at a time. And even the sum bits, that is the 4-bit sum, is available at a time with the 4 sum outputs of full adders. So, and hence we are calling it as parallel adder. It performs the addition of all the bits at a time, or else parallelly. So we are calling it as parallel adder. So here let us consider, this is a full adder which can add the LSBs. So as I told you that here, while adding LSBs, we can take the carry input as 0. So the carry input is 0. And it produces the carry, the full adder produces the sum output as well as the carry output. So the carry output of first full adder is given as the carry input to the second full adder. And again, the second full adder performs the addition of A1, B1 and C0. Okay. So then it produces the output, that is sum S1 and carry C1, where the carry C1 is given as carry input to the next full adder, and where this full adder performs the addition of A2 plus B2 and C1, which is the carry input to the third full adder, and produces 2 outputs, sum S2 and carry C2. So the carry may be either 1 or 0. It will be forwarded to the next section. So here finally we are going to take the carry output from the last full adder. So the carry output of the last full adder is taken as C out of the addition, and the 4-bit sum is available at the sum outputs of all the 4 full adders. So this is a 4-bit parallel adder. Okay. So C0, C1, C2, C3 are the carry inputs which are connected together as a chain using full adders. So then C4 is the output produced by the last full adder, where C out is the first full adder is connected, C out of the first full adder is connected to the C in of the next full adder. This is nothing but the cascading, where the sum output, that is S0, S1, S2 and S3, are the sum outputs that produce the sum of organ and addend bits. As you all know that A plus B, so where A is called as organ, where A is called as organ and B is called as addend. The number which is going to be added is addend, and to which we are adding is organ. Okay, so sum output of organ and addend bits. The inputs for the inputs for the input variable A and B are fetched from the different source registers. For example, the bit for the input variable A comes from register R1 and a bit for the input variable B comes from the register R2. So here some mechanism, we need to have some input source for providing the inputs, right? Those are nothing but registers. I can get A from one register called R1 and I can get the value of B from another register called R2. So the outcome produced by adding both the input variables is stored in the third register, that is, or to one of the source register. I can use another register for storing the sum of the, that is sum output of the adder, or else I can use any one of the source register. That means either R1 or R2 I can use, or else I can go for a new register for storing the sum output of this addition. Okay, so that is binary parallel adder. So what are the advantages or advantages that you can observe over serial adder in a parallel adder? So as we can see that a parallel adder circuit performs the addition of all the 4 bits of data parallelly at a time. So the time required for performing the addition is less. Whereas in serial adder, the full adder has to perform the addition in 4 clock cycles. Whereas in this one, at a time all the inputs are applied, but inputs are applied and the outputs are also available at a time once we apply. So only the thing is, it requires a small amount of time in order to apply the output, the carry output of one full adder to the carry input of the other full adder. So that means there is a propagation delay of carry from one section to the other section. So if we compare the delay of this parallel adder with respect to the serial adder, so where the serial adder requires 4 clock pulses, whereas the parallel adder requires, this can perform the addition operation in a single clock cycle, but only the thing is, it has propagation delay too. Only the delay is due to the propagation of carry from one section to the other section. But all the other outputs or inputs are applied at a time, at a single time. Okay, at a single instant of time. So that is a difference that we can observe. And here, as we have seen the block diagram, so as the number of bits to be added is increasing, the number of full adders required are also increases. So that means the cost of this parallel adder is high when compared to the serial adder, whereas the serial adder requires only one full adder and one delay circuit. So, but the cost of parallel adder is high when compared to the serial adder, but the delay or else the time required for performing the addition of 2 numbers is less in case of parallel adder when compared to the serial adder. Now, let us see the binary subtractor. So, the binary subtractor, as we all know that, so we can perform the subtraction operation by with the help of adder. How can we perform the subtraction using adder? So only the thing is, we need to get the complement of negative number. So the complement of negative number is nothing but a positive number. So by finding the complement of negative number, or else by so whenever you are performing the subtraction, this is called as a, when I am performing a minus b, a is called as minuend and b is called as subtrahend. So by finding the complement of subtrahend, the subtraction can become into addition. So I can perform the subtraction even by using a parallel adder. Only the thing is we need to get the complement of negative number. So the circuit for performing the subtraction, binary subtraction, is same as binary parallel adder. Only the thing is all the B inputs are applied to the full adder circuit by complementing it using an inverter. So each full adder, before applying the input B to the full adder, that B is getting complemented because this B is a negative number, so that I am going to convert it into positive number, so that the subtraction is converted into addition, and which can be performed by the full adder circuit. So I wanted to say the parallel subtractor can be designed in several ways, including the combination of half adder and half subtractor and full subtractor, and all subtractors also you can use. But in order to reduce the number of circuits required, so I can even perform the subtraction using the adder. Only the thing is by subtracting by complementing the subtrahend, and the complementation of subtrahend can be done with the help of inverter or else NOT gate. NOT gate is nothing but an inverter which can get the ones complement of the negative number so that it can become positive number, and hence I can perform the addition subtraction even using the same circuit which is known as parallel adder. So this is a parallel subtractor circuit where this is the 4-bit parallel subtractor, sorry 5-bit parallel subtractor, where I can have one full adder for performing the subtraction of 2 bits of 2 binary numbers. So this is the parallel subtractor here. So the parallel binary subtractor is formed by the combination of all full adders with subtrahend complement input. So by complementing the subtrahend input, we can design a parallel subtractor. So the operation considers that the addition of minuend along with the 2's complement of subtrahend is equal to their subtraction. So that means the addition of minuend along with the complement of subtrahend is equal to their subtraction. So that is parallel subtractor. So firstly, the ones complement of B is obtained by using NOT gate, and 1 can be added through the carry. So the thing is, here I want to get the 2's complement. So what is 2's complement? 2's complement is nothing but 1's complement plus 1. How can I get the 1's complement? By using NOT gate. What is the operation of NOT gate? It just complements 1's to 0's and 0's to 1's. So in the given data, if 1's are there, it will be complemented into 0's using NOT gate. So I want to get the 2's complement. So the 1's complement plus 1. So that means this 1 is to be added to the least significant bit. So that is why the least significant full adder is applied with carry input which is equals to 1, so that the 2's complement of the given number is obtained. Okay, so that is the thing here. So the 1's complement of binary is obtained, that is B can be obtained by using NOT gate, and a 1 can be added through the carry to find the 2's complement of B. This is further added to A to carry out the arithmetic subtraction. So now first we are getting the 2's complement, and then adding it to the A will give you the arithmetic subtraction of A and B. So this process continues till the last full adder, that is nth full adder, uses the carry bit, that is Cn, to add with its input An and 2's complement of Bn to generate the last bit of output along the last carry bit, that is Cout. So this is the procedure, binary subtraction. So now binary adder or subtractor is a combination of 4 full adder. Okay, so here that is about binary subtractor. So I can have one more provision that I can implement. So in this case, what you can understand here, the binary adder or subtractor can be designed separately, where the binary adder can have only full adders, whereas a subtractor requires inverters also. Instead of having separate circuitry, I can have a single circuitry which can perform the binary addition as well as the subtraction. So that is, a binary adder subtractor is a combination of 4 full adders which is able to perform the addition and subtraction of 4-bit binary numbers. Now my aim is to design a single circuit such that it can perform the binary addition as well as the binary subtraction. So this is the this can be done by using a control line which determines the type of operation being performed. So that means whether I'm going to perform the subtraction or addition operation is decided by an extra input which is called as control line. This determination is done by the binary values 0 and 1 which is held by k. So here this is the binary adder or subtractor. That means with this circuit I can perform, with a single circuit I can perform the binary addition as well as the binary subtraction. So as I told you that we can have a control input so that the type of operation can be decided. So here the control input is k. Based on this k input, I can decide whether it is performing the binary addition or subtraction. So how can we decide the operation of this one? So if k is equals to 0. So along with this full adders, I can have XOR gates. So XOR gate is applied to input y here. So now I can perform the operation, that is x plus or minus y. When it can perform the x plus y, and then when it can perform the x minus y. So here one input to all the full adders is one of the bits of x, that is x0, x1, x2, x3, where before applying the y input to the full adder, it is first applied to the exclusive OR gates, where the other input to the exclusive OR gate is k, where k is a control line. For example, if k is equals to 0, then what happens when y naught is equals to 0, then what happens? As it is 0 and it is 0, the output is also 0. For example, if y naught is 1, then what happens? This is also 1. So that means if k is equals to 0, the y input is applied to the full adder as it is. Is it or not? So if y is 0, that is applied to the full adder. If y is 1, the output of the XOR gate is also 1. So that is how when k is equals to 0, it applies the y input as it is and performs the binary addition. Okay. Now what happens when k is equals to 1? Now let us say that k is equals to 1 now. When k is equals to 1, one of the input to the XOR gate is 1. Right? Now what happens if y naught is equals to 0? As it is 1, when y naught is equals to 0, the output is equals to 1. When y naught is equals to 1, then the output is equals to 0. Right? So what is happening here? When the input is 0, it is getting complemented. When the input is 1 and it is applied as 0 to the full adder. So that means when the k input is 1, y is getting complemented and applied to the full adder. That means it performs the subtraction, binary subtraction. Okay. So here I can understand that by taking k is equals to 0, it performs the addition because y input is applied as it is. Whereas when k is equals to 1, the y input is applied to the full adder in its complemented form. So as it is complemented, what we can say that this full adder performs the subtraction operation. Okay. So that is how a single circuit with exclusive OR gates that can perform the binary addition and subtraction, both the binary addition and subtraction, where the binary addition can be performed when k is equals to 0 and binary subtraction operation can be performed when k is equals to 1. Okay. So that is the binary adder or subtractor. Remaining everything is same, right? Only the thing is we need to use XOR gates. So what is our aim? That means in order to avoid the separate circuitry for performing the addition and subtraction, I'm designing a single circuit which can perform the binary addition and subtraction. So this addition and subtraction can be performed based on the control input k. If control input k is 0, then the y output is applied to the full adder as it is, and hence it can perform the binary addition. When k input is 1, then the input y is complemented and applied to the full adder, and hence we can say that it performs the subtraction operation. So that is the binary adder or subtractor. So now let us see the advantages of parallel adder or subtractor. So what are the advantages? Why we are going for parallel adder? Why we are performing the addition and subtraction parallelly? So the first advantage is the parallel adder or subtractor performs the addition operation faster as compared to the serial adder or subtractor. Because in serial adder, all the bits are applied bit by bit. That means in order to perform 4-bit addition, it requires 4 clock pulses, whereas parallel adder, all the bits are applied to the adders at a time, at a single instant of time. But even though there is a propagation delay of carry from one section to the other section, this propagation delay is less when compared to the serial adder. So the time required for addition does not depend on the number of bits here. Only it depends upon the propagation delay. That means how much time is required for transferring the carry from one section to the other section, where it does not require on the number of bits to be added, because all the bits are added at a time. So whereas in serial adder, as the number of bits increasing, the time required for performing the addition also increases, but it is independent of number of bits, because all the bits are applied at a time, and hence the time required for performing the addition is independent of number of bits. The output is also taken in parallel form, that is all the bits are added or subtracted at the same time, and it is less costly. And it is less costly when compared to this any other adder. It is less costly, and those are the advantages of binary adder or subtractor. Now coming to the disadvantages. What are the disadvantages? So each adder has to wait for the carry which is to be generated from the previous adder in the adder chain. So that is what I said. The carry has to propagate from one section to the other section. So that is what the delay, that is a drawback of parallel adder. The propagation delay, that is the delay associated with the traveling of carry from one section to the other section, is found to increase with the increase in the number of bits. As the number of bits are increasing, in order to get the final carry, I have to wait. The carry has to reach the last section of full adder. So as the number of bits to be added are increasing, so this propagation delay becomes disadvantageous. So that is about the serial adder, parallel adder, and binary adder or subtractor. I hope you can understand. Now, magnitude comparator. What is a magnitude comparator? A magnitude digital comparator is a digital combinational logic circuit that compares two digital or binary numbers in order to find whether one binary number is greater than or less than or equal to the other binary number. So what we are doing, I am comparing two binary numbers, A and B. So the A may be either greater than B, or A may be either less than B. Okay, A may be either greater than B or less than B, or A may be equal to B. So this that means here what I am saying, whenever we are performing the comparison operation, there are three possibilities of outputs. One is A greater than B, A less than B, and A greater than B. So whenever I am comparing two numbers, there are three possibilities. That is, A may be either greater than B, or A may be either less than B, or A may be equal to B. So here, this is a combinational logic circuit which can perform the binary, which is used to find whether one binary number is greater or less or equal to the other binary number. right? Now coming to the block diagram. So as I told you that it is a combinational circuit. It does not depend on the present state or its previous output. So we have two inputs here and three outputs. So the two inputs may be of any bit here. So the two inputs may be of any bit, either it may be 1 bit or 2 bit or 3 bit, whatever it may be. So whatever the number of bits that each number is having, whenever you are comparing two binary numbers, it can result three outputs: A greater than B, A equal to B, and A less than B. So this is a block diagram of a comparator. So the possible sizes of comparators are, we can have two binary numbers of 1 bit each, or 2 bits each, or 3 bits each, and so on. So a comparator used to compare two bits, that is two numbers, each of single bit, is called as single bit comparator. So now let us see the block diagram of single bit comparator. So as I told you that whatever it may be the number of bits in the input, we have three possible outputs whenever we are performing the comparison. So three outputs: A less than B, A equal to B, and A greater than B. So this is a block diagram of comparator, one bit comparator. So A, B are the inputs, and three outputs we have: L, E, G, that is A less than B, okay, A equal to B, and this one is A greater than B. So this is the block diagram of single bit magnitude comparator. Now let us try to implement magnitude comparator, which can compare two single bit binary numbers. So now let us draw the truth table for a single bit comparator. So the single bit, as I said you that we have two inputs A, B, which are of single bit each. So we may have four possible combination: 0, 0, 0, 1, 1, 0, 1, 1. So these are the inputs here, possible inputs. So now I want to decide whether A is greater than B, or A equal to B, or A less than B. So when A naught, B naught equal to 0, 0 and 1, 1, when both the inputs are equal. So when both the inputs are equal, then the output A equal to B will be high and the remaining two outputs will be low. And similarly, A naught, B naught equals to 0, 1, and B is more than A, and hence A is less than B. So here, in case of this one, A naught, B naught is equals to 0, 1. So we may have another value for A. So here, if you see, these are the two single bit numbers, as A naught is 0, where B naught is 1. So that means what I can say? I can say that A is less than B. So A is less than B is active, and the remaining two are 0, okay, or else inactive. So when A naught, B naught is equals to 1, 0. So that means A naught value is 1 and B naught value is 0. So that it indicates that A is greater than B. So in this condition, A is greater than B output is high and the remaining two outputs are low. So this is a truth table according to the logic which we have discussed now. Two single bit inputs, A naught, B naught, and these are the outputs. So these are the outputs and this is the input. This is the input here. So when A naught, B naught, 0, 0, so equal to, both A naught and B naught are equal. So equal to is 1, remaining two are 0. Next, A is 0 and B is 1. A is less than B. So A less than B, and B and Z are 0, 0. Now 1, 0. So again A is greater than B. Okay. Because A value is 1, B value is 0. So A greater than B is 1. Remaining two are zeros. And both are same here. So A equal to B is 1. And A less than B is 0. And A greater than B is also 0. Now what I want to do, I want to implement the logic circuit for this single bit comparator. So how many outputs we have? Three outputs, L, E, G. Now for that, for getting the expression for L, E, G, so we have to take a K-map, where K-map is having, inputs are two input variables we have. 4 cells we have. First one, I am writing the K-map for L. So when the L output is becoming 1, when A naught is equals to 0 and B naught is equals to 1. So only one combination. So I can write it, I can write this one as A naught complement B naught. A naught complement B naught. And similarly, now let us see, A equal to B is 1 for 2 combinations. So what are the 2 combinations? A naught, B naught, and next one is A1 equal to 0 and B1 is also equal to 0. So as A naught, B naught both are 0, so I can write the minterm for this one as, so I can write this equal to as A naught complement B naught complement plus A naught B naught. So this is for equality. Now coming to the greater. So only greater output is 1. That means A is greater than B. 1 only when A naught is equals to 1. So G is equals to A naught complement. A naught plus B naught complement. A naught plus B naught complement. Because this is 1 for the combination of A naught 1, B naught 0. So A naught 1, so A naught plus B naught complement. So this is the single bit magnitude comparator. Now let us draw the equation. So here I am writing the equations from the thing which we have discussed just now. So A naught less than output is equals to A naught complement B naught, A naught complement B naught, and greater than is equals to A1, sorry, A naught, this B1, A naught, sorry, G, A naught equal to 1 and B naught equal to 0. So A naught, B naught complement. And now coming to the equal to. So equal to, so for 2 combinations the equal to output is 1. A naught 0, B naught 0. So equal to is equals to A naught complement, B naught complement plus A naught, B naught. So this is the equation. I can also write this equation as A XOR B whole bar or A XOR B. So this is the output equation. So now A naught less than B naught, that is L output is equals to 1 when A naught bar plus B naught. A naught bar plus B naught. This one. A naught bar plus B naught. Right? Now coming to A naught, which is B naught equal to E. So A0, B0. So this is plus A0, B0. So I can write this one as A XOR B whole complement, or else I can write this one as A bar B plus, sorry, A naught bar. A naught bar, B naught bar, A naught, B naught. So I can write this one as A naught, B naught complement plus A naught complement B naught whole complement. So I will get this NOR implementation. So that is A naught, B naught complement, A naught complement, B naught complement plus A naught, B naught. So that's it. That is this one. And greater than, when the greater output is equals to 1, greater output is equals to 1 when A naught is equals to 1, B naught is equals to 0. So A greater than B, so G is equals to A naught greater than B naught, so which is A naught greater than B naught. Okay, A naught greater than B naught is equals to 1 only for one combination, 1 0. Only for one combination, 1 0. A naught into B naught complement. So this is the output. These are the Boolean expressions. Now coming to the logic circuit, based on this Boolean expression, we will draw the logic circuit using basic logic gates. So first, AI complement, okay, AI complement, and this one is BI. So AI complement plus, sorry, into BI, and this one AI into BI complement. This is BI complement and this one is AI complement. Sorry, not complement, this is AI. So now this is given, as, so what is less than? Less than output is A naught complement B naught. A naught complement B naught. Okay, so this is less than, or else AI complement into BI. Next, greater than, A naught B naught complement. So that is AI into BI complement. This is greater than. Coming to equal to, so what we are getting? AI complement into BI, and this one is AI into BI complement. Now, NOR gate it is AI complement into BI plus AI into BI complement whole complement. Now expand this one, AI complement into BI into whole complement into AI plus BI complement whole complement. So what I can get here? I can get here is A BI complement, sorry, A plus BI complement into A complement plus BI. So now if I expand this one, I will be able to get AI BI plus AI complement into BI complement. So that is nothing but XNOR gate. Simply you can draw XNOR gate also. So this is the implementation of 1-bit comparator. So now let us see the 2-bit magnitude comparator. So that means whatever it may be the number of bits in each number, the comparator performs the comparison operation. It compares the two binary numbers and produces three possible outputs. What are the three possible outputs? Less than, greater than and equal to. So as we have two 2-bit binary numbers, what are the possible combinations of input we may have? So 2A, that is A1, A0 and B1, B0. So that means totally how many input variables we have? 4. So 16 combinations we may get. 16 combinations, right? And finally the outputs are three outputs: A less than, A greater than and A equal to B. So the 2-bit comparator compares two binary numbers, each of 2 bits, and produces their relation such as one number is equal or greater than or less than the other. So the first number A is designated as A equals to A1, A0, and the second number is designated as B, and this comparator produces the three outputs: greater than, less than and equal to. So greater than is equals to 1 when if A greater than B, and equal to is equals to 1 when if A is equals to B, and less than B. So now let us see the block diagram. So as I told you that we have 4 inputs here because two numbers are binary, okay, which are having 2 bits each. So A1, A0, this is related to A, and B1, B0 are related to B. And this is a 2-bit magnitude comparator. Finally, we have 3 outputs: A less than, A equal to and A greater than B. So now coming to the truth table. As we have 4 inputs: A0, A1, B1, B0, and 3 outputs: A equal to B, A less than B and A greater than B. So list out all the 16 possible combinations of this. So that is 0000, 0001, 0010, 0011 and so on 1111. Now I am going to discuss the operation of this 2-bit comparator, right? So the 2-bit comparator mainly, so here if you look at this truth table, if A1 is equals to B1, A1 is 0000. So what is the decimal equivalent of this 0? And this is also 0. Whether A is greater than B? No. A is less than B? No. A is equals to B? Yes. A equal to B output is 1 and the remaining all are zeros. Similar fashion, if A is equals to 0, B is equals to 0 and this one 0, 1. So and hence the what is that? So A is 0, the decimal equivalent, whereas B is 1. So that means is A is greater than B? No. So that is why A greater than B is 0. And is A less than B? A is less than B? Yes. A is 0 whereas B is 1. So A is less than B. So A less than B is 1 whereas A greater than B is 0. So like that we can find out all the outputs for all the input combinations. For example, let us take 1100. What is 11? 11 means 12 whereas 00 is 0. So 12 is greater than B. So that is why A greater than B is 1 and the remaining 2 are 0. So like that we can frame the truth table for 2-bit magnitude comparator. And based on that we can have the mathematical or else mathematical expression, and also we can draw the logic circuit by getting the simplified Boolean expression. So for that what I am doing, I want to draw the K-map. I want to draw the K-map here. So how many variable K-map is required? The size of the K-map is decided with respect to the number of input variables. How many input variables we have? 4 input variables we have. Okay, 4 input variables. What are those? A1, A0, B1, B0. So that is why, in order to find out the simplified Boolean functions for the 3 outputs of comparator, that is A less than B, A greater than B, and A equal to B. First, let us derive the equation for A greater than B. So what is the order that is given in truth table? A1, A0, B1, B0, right? So this is 0, 0, 0, 1, 1, 1, 1, 0, 0, 0, 0, 1, 1, 1, 1, 0, right? So now let us identify for which combinations the A greater than B output is 1. So here this is the first combination. Let me erase all these so that you can easily understand. So for which combinations it is 1. So this is the combination for which the A greater than output is 1, B output is 1. So next this one, this one, this one, right? So here, now what is the combination? 0, 1, 0, 0. 0, 1, 0, 0. 0, 1, 0, 0 means 4. This is 0, 1, 3, 2, 4, 5, 7, 6, and then 8, 9, 11, 10, 12, 13, 15, 14, right? So now I want to map this A greater than B to the K map. So A greater than B is 1 for the combination 0, 1, 0, 0, that is 4. Next up, this is 1, 0, 0, 0, 8. Next, 9, and next 12, next 13, next 15. So these are the combinations for which the A greater than B output is 1. Now let me group these into now let us form a quad with these 4. Okay, and then I can form a pair. I can form a pair here. I can form a pair here. So that the equation for this one, first this one, A1 value is 1. So A greater than B is equals to A1. Okay, so where for these two cells, A1 value is common, A1. Next, for these two columns, B1 value is varying. B1 value is common, B0 is varying. Eliminate B0, consider B1. B1 value is 0. So B1 complement. Okay, now coming to this one. What is a prime implicant for this? A1, A0 are common, A1, A0. And coming to these two cells, so here B1 value is varying, eliminate B1, B0 value is common. So B0, A1, A0, B0. And coming to this one, here A0 value is common, so I just consider this A0. Okay, and coming to this one, B1 complement, B0 complement, right? So these are the equations for the A greater than B. So like that, similarly, we can also derive the expression for A1. So this is the K map for A equal to B. A equal to B. Now let us identify all the combinations for which A is equals to B. So first this one 0, 0, 0, 0. Next this one 5, and then this one, and then this. So these are all the possible combinations for which the A equal to B output is equals to 1, 0, 0, 0, 1, 1, 1, 1, 0, 0, 0, 0, 1, 1, 1, 1, 0. Now let us map this. This is 0, okay, 1. Next 5, that is 5, and then 10, that is 8, 9, 10, 11. So 10, and next thing is 15. So this is 15, right? So these are all the values here. So now I cannot simplify this one because there are no adjacent cells. So we have to take as it is. We have to take as it is. So now A equal to B output will become, so A1 complement, A0 complement, and then B1 complement, B0 complement, right? Plus this one, A1 complement, A0, okay? Because this is, sorry, okay. A1 complement A naught plus sorry, not plus, because this is a cell cover, this is the one covered by these two. So A1 complement A naught, B1 complement B naught. Like that, we have to write down all the equation. And for this one, A1 A naught, next B1 B naught plus. For this one, A1 A naught complement, okay, and then B1 B naught complement. Right? So this is the equation for A equal to B. And similarly, we can also draw for A less than B. So now A less than B. So for that, I'm taking a K-map again here. 4 variable K-map. This is for A less than B. So A1 A naught, B1 B naught. So 0 0 0 1 1 1 1 0. 0 0 0 1 1 1 1 0. Now let us see for which combinations this is equals to 1. So this is 1, 2, 3, 1, 2, 3. Next 6, 7, and then 11. 6, 7, 11, right? 1, okay, 2, 3, and then 6, 7. 1, 1, 0 is 6, 1, 1 is 7, and then 11, right? 1, 2, 3, 6, 7, 11. So 1, 2, 2, 3, 6, 7. Let me write with another color. So 1, 2, 1, 2, 3, 6, 6, 7, and then 11. 6, 7, then 4, 5, 6, 7, 8, 9, 10, 11. 11, 10. Right? So these are the values here. Sorry, not 11, 10. It is only 11 and 15. 11, only 11. Only 11. Only 11. So total how many combinations? 1, 2, 3, 6, 7, 11. 6, 7, 11. Okay. So now I can form a quad with this. And then similarly I can form a pair with these two, and even I can form a pair with these two. So now this expression can be for this one, A1 complement into and B1. Okay. Now for this one, this pair A1 complement A naught complement, and for this pair 0, A1 is varying, eliminate, A naught is common, so A naught complement. And coming to this, okay, just a second. So here, this is A1 complement, A naught complement, and B1 is varying, B naught is common, so B naught complement. And coming to this one, A naught complement, and then B1, B naught. So this is A equal to B. So not A equal to B, A less than B. So A less than B is equals to, what is the equation we have got? A1 complement B1 plus A1 complement A naught complement B naught complement plus A naught complement B1 B naught. So this is the equation. So once this is done, we can simplify the Boolean function. So these are all the Boolean expressions here which we have got by drawing the K-maps and all. So these are the Boolean functions. So here A equal to B can also be simplified as A naught X nor B naught into A1 X nor B1. So this is the equation for A equal to B. So the remaining all can be written as it is, right? If you look at this, one, A1 complement B1, okay, A less than B, A1 complement B1, A naught complement B1 B naught, A1 complement A naught complement B naught, A1 complement B1 B naught, A1 complement A naught complement B naught. Okay, so that is the answer. Finally, I can implement the Boolean logic circuit based on that Boolean function. So this is the magnitude comparator expression. So I have taken all the 4 inputs and their complements here. So this line indicates A1 and this line indicates A1 complement. Similarly, A0, A0 complement. B1, B1 complement. B0, B0 complement. Right? So just provide the connections to all the AND gates. So this is A greater than B, A equal to B, and A less than B. So once you have got these expressions, no, so you can easily draw the logic function. So if you look at this one, A0, B1 complement, B0 complement. A0, B1 complement. Okay, this is A0, B1 complement, B0 complement, first term. And coming to the second term, A1, B1 complement. A1, B1 complement. This is A1 and this one is B1 complement. This one is A0, B1 complement, B0 complement. And coming to the third term, what is the third term? A1, A0, B0 complement. A1, this is A1, this is A0, and this one is B0 complement. So this is how we can get the logic function, the logic circuit. So this is the magnitude comparator, right? So here, the magnitude comparators are mainly used to compare the two numbers which can produce the three possible outputs, that is the A greater than B, A less than B, and A equal to B. Now what are the applications of comparators? So the comparators are used in address decoding, circuitry, in computers and microprocessors based devices, to select a specific input or output device for the storage of data. That means in order to, so whenever you are dealing with computer, so we have some input devices and we have some output devices. So each input device will have its own address. To select a specific device, we need to decode the address. For that address decoding purpose, which can be done in computer or microprocessor circuitry, we'll use this comparator. Now, the another application of this comparator are, these are used in control applications in which the binary numbers representing the physical variables such as temperature, position, etc. That means in case of temperature control and position controls also, we can find the applications of comparators. So that means, for example, temperature control, what we are going to do? We have two temperature, required temperature and actual temperature. We'll be comparing them. So if these are not equal, for example, we have AC, right? The room temperature and the expected temperature are compared. If they are not equal, the AC will be on. So there, like that, position control or temperature control or some controlled applications, we can use this comparator, where the controlling can be done by comparing two quantities, right? So, etc. are compared with the reference value. Then the outputs from the comparator are used to drive the actuators. These are actuators so as to make the physical variables closest to the set or reference values. So by comparing them, we will be adjusting the temperature. Not only the temperature, even the position can be adjusted by comparing with the reference value. So these are the applications of comparators, and we can also use this comparators in process controllers and servo motor controls. So these are the applications of controllers. So this is about comparator and binary adder and subtractor. Even we have seen parallel adder, serial adder, and what are the advantages of adders, binary adders. That is, either it may be a serial adder or parallel adder. And we have seen the comparators also. So you can design any comparator which can be able to compare any two numbers of any length. That means that may have any number of bits. Okay. So this is about the binary adders and comparators. I hope it is clear to you all. That's all for this lecture. Thank you, Anand.
Like, share and subscribe. Hit the bell icon for more updates.